This is a brief video to go through the results you got in your lab 2, or that most of you got in your lab 2. The key of lab 2 and what you have seen is the concept of bifurcation. First of all, let's look at the phase line. The phase line is a condensed version of the direction field. It's just a line instead of a full field, and what you are plotting y and are indicating the equilibria that y has as points on this line, and you want to give an information about the direction of the solution. In the same way as in the direction field, you start looking at where equilibria lies, because that makes the horizontal lines of our direction field, and then you want to see the sign on where the solution goes towards, so the sign of the derivative of the solution. This is also what a phase line looks at. While in the direction field, we want also a next step, that is, how big is the derivative of our solution? This information is not in the phase line. So in the phase line, we only have information about, is the solution growing or is the solution decreasing? And we can draw it by arrows. In your MATLAB code, instead of writing arrows, you use colors, blue and red. I think I got it right. So blue is where the solution is growing, red is where the solution is decreasing. If you look at the equilibria and the phase line, you can immediately determine if an equilibrium that you're looking at is stable, unstable, or something else. So for example, here we have on the left an unstable equilibrium, because on both sides of the equilibrium things are moving away from it. On the right side things are growing away, on the left side things are decreasing away. In both cases they're tending away from the equilibrium. So that equilibrium is unstable. On the right of our diagram we have another equilibrium that is stable. On both sides of the equilibrium, things tend to the equilibrium. That makes the equilibrium stable, because if you start in the neighborhood of the equilibrium, so not too far from the equilibrium, you tend to it. While the equilibrium in the center of our diagram, of our phase line, it's semi-stable, half stable. This is because on both sides of the equilibrium, the derivative of y, f of y, is positive. So on both sides of this equilibrium, the solution y tends to the right. That means that if you start on the right of this equilibrium, you tend to this equilibrium. But if you start on the left, you tend to this equilibrium because you're moving towards the right. But if you start on the right, you keep moving towards the right, so you move away from it. On one side of the equilibrium, you're moving away. On the other side, you're moving towards. That makes for a semi-stable equilibrium. We also talked about, in lab 2, ODEs that depend on a parameter. So in class we have talked a lot about y prime equals f of y, while in the lab we talked about y prime equals f of y and alpha. And alpha is called a parameter here. Alpha can enter into the definition of the ODE and change things. And an important statement is that the phase line can change depending on alpha. For example, let's look at this situation. We have y prime equals y minus alpha. So our right hand side is a function of y and alpha that is just the difference between y and alpha. If we look at it, if we draw it with respect to y, f of y depends on alpha, and depending on alpha, f of y it's a higher line or a lower line. When alpha is equal to 0, f of y is y itself, so it's a diagonal. For alpha positive, you're lifting this line up. For alpha negative, you're shifting it down. Still the same shape of a line, but you're moving things around. So your equilibrium changes. For your equilibrium, in this case, is y equals to alpha and moves depending on where alpha is. In all the cases you still have one unstable equilibrium. Let's look at another example. a bit more complicated. Here we have as right-hand side y times y minus alpha. So again, our right-hand side depends on y and depends on alpha. If we solve this, we see that the equilibria are y equal to 0 and y equal to alpha. If alpha is equal to 0, that means there is only one equilibrium. So we see the difference between all the values of alpha that are not 0 and the one value of alpha in which alpha is equal to 0 and we only have one equilibrium instead of two. So if we plot our phase line depending on alpha, we see that for alpha positive, we have two equilibrium, y equal to 0 and y equal to alpha, that is on the right side of y equal to 0. On the left of y equal to 0, we are tending to 0. Between 0 and alpha, we're tending to 0. And for anything bigger than alpha, we're tending to infinity. When alpha is equal to 0, you will notice that the right-hand side of your ODE, f y alpha, becomes y squared. Y squared is either 0 or positive. So everything has either a 0 derivative, that is at y equals to 0, or y equal to alpha because alpha is equal to 0. Everything else is tending to the right. And if alpha is negative, we first have the equilibrium y equal to alpha, then we have the equilibrium y equals to 0, and outside of y equals to of the interval alpha to 0, outside of that, everything tends to the right. While between alpha and 0, we go to the left. So if you look at this phase lines, you notice that at the top, y equals to 0 is a stable equilibrium, while y equals to alpha is unstable. And for alpha equals to 0, y equals to 0 is a semi-stable equilibrium. While for alpha negative, we have a switch with respect to alpha positive. Now we have y equal to alpha being stable and y equals to 0 being unstable. We want to show this information in a way that is more readily available. So we draw what is called a bifurcation diagram. We write on the horizontal axis the parameter that we're looking at, and on the vertical axis we're looking for y. But on this diagram we're only going to look at equilibria. So we want to draw the equilibria of this diagram. We have y equal to 0, that is horizontal, and y equal to alpha, that is the diagonal. And then we ask ourselves, if we start away from this equilibria, where is our function going towards? So in this case, you have to think that alpha is a value and y has only the option of going up or down for a given value of alpha. So in a certain sense, each strip of this bifurcation diagram is a phase line. So we're giving here the information about where y is going when it's not at the equilibrium. And here we retrieve the three directions that we saw before. For alpha negative, if we start lower than alpha for y0, we tend to alpha. If we start between alpha and y equal to 0, we tend to alpha. And if we start outside of that, we grow up. Then we have the information that y equals to 0 is semi-stable at alpha equal to 0. This is given by the information that you see that everything under everything, in a certain sense, tends up. And everything over y equal to 0 and y equals to alpha also tends up. So if you're at the intersection, you have things underneath going up and things over going up. So y equal to 0 for alpha equal to 0 is semi-stable. Then if you move further on, you see that you have the two equilibria, y equal to 0 and y equal to alpha, on the right of our diagram. Between them, you tend down. Outside of them, you tend up. Here we see what bifurcation is happening. Bifurcation means that the structure of your equilibria is changing. In this case, it is changing at y equals to 0, alpha equal to 0, because it's the one point in which we have one equilibrium instead of two equilibria, and the stability of the equilibria is changing. For alpha negative, y equal to 0 is unstable. Afterwards, it is stable. For alpha negative, alpha is a stable equilibrium. For alpha positive, alpha is an unstable equilibrium. So we have a change locally, just for alpha equal to 0, we have a change in the number of equilibria, and globally we have a change in the stability of the equilibria. Let's look at another example. We have now y prime equals to y squared minus alpha. What sort of equilibria do you have? Well, y equals to 0 is always an equilibrium of this ODE. But the second equilibrium would be y squared equal to alpha. So y equals plus or minus square root of alpha. That is an equilibrium only if alpha is positive. Might be equal to 0, but in that case it overlaps with the other one. So we have a situation in which two equilibria exist only for some values of alpha and not for all of them. Let's try to see how this right-hand side looks. So I've drawn for alpha negative, for alpha equal to 0, and for alpha bigger than 0. For alpha negative, it's a swing, it's a third order polynomial in which alpha is somehow pushing you even faster. So you have this S that touches the horizontal axis in only one point. At alpha equal to 0, you have a very similar S. The only tiny difference is that at y equal to 0, you're flat. First and second derivative at alpha equal to 0 for y equal to 0 are 0. For alpha positive, you have a really S-shaped thing that crosses the 0 axis 3 times. 1 at 0 and 1 at square root of, and 2 at plus or minus square root of alpha. If we look at equilibria here, we find them very easily, and then we can find the phase line. For alpha negative, y equal to 0 is unstable. For alpha equal to 0, y equal to 0 is again unstable. For alpha positive, y equal to 0 becomes stable. And we have two new equilibria, plus or minus square root of alpha, that each is unstable. If we want to draw all of this information together in a bifurcation diagram, what we see is this. On the horizontal axis, we have alpha. On the vertical axis, we have y. Horizontally, we have always the equilibrium y equal to 0. And then we have a parabola with respect to alpha. That is, the equilibria plus or minus square root of alpha that appear only for alpha positive. Then we can also draw where the direction field is bringing us. For alpha negative, it's bringing us away from 0. For alpha positive, locally is bringing us towards 0. And if you're outside of the parabola plus or minus square root of alpha, it's bringing us away. One thing that you notice when direction fields are drawn is that if you have divided an area by equilibria, the rule connected area with no equilibrium that is cutting through has the same direction. So for example, here the area that is bigger than y equal to 0 and square root of alpha, so the area that is on top of our horizontal axis and on top of the parabola, has everything tending to plus infinity. The same thing, the opposite thing we can say about the thing that is under y equal to 0 and under the parabola. Everything that is under that tends to minus infinity. So once you know all the equilibria and you have drawn them in your bifurcation diagram, knowing one phase line gives you information of all the connected areas next to that phase line.